Yep. Hello everyone and a warm welcome to our Learner Space course, Introduction to Astronomy and Astrophysics. So this is bound to be a very exciting course. We'll be learning the fundamentals of astronomy and astrophysics, and today is the first session which we'll conduct, and it is on the topic of telescopes. I am Arnav Jaiswal. I'm a part of Team Kritika, and I'll host a session today. And let me just share my screen before we start. Just a sec. Yeah, can you see my screen?
Yes.
Yeah, okay. Okay. Welcome to Telescopes, everyone. When you think of astronomy or astrophysics, I'm pretty sure the first thing that comes in your mind is probably just a star child who's on his knees and just looking at the stars through a telescope. Telescopes and astronomy are inseparable, and telescopes are one of the most important factors in astronomy. And it is very important that we learn about telescopes and get into the depths of astronomy and astrophysics. Let's start our telescopes. And if you have to learn anything about telescopes, we'll have to start with light. We have studied about for probably years and years since sixth grade. We have studied about light, but let's just have a quick recap of what light is. Light, as we know, has is also shown to as known to show wave nature and also particle nature. Wave nature of light is shown by diffraction, and particle nature of light is shown by
Arnav, you're muted.
Oh, okay. Can you see my screen?
Yeah, the screen is visible. Just restart from the previous slide.
Oh, I'm so sorry. Yeah. Okay. So where did you cut where did you where was I cut off? Uh, so I'll start from this slide. Yeah. So I'm sorry for that, but yeah. So when we look at light,
Where did you?
yeah. Can you repeat that? Hello.
No, carry on.
Yeah. We were looking at the wave nature of light, which is exemplified by two phenomena, which is diffraction and interference. Diffraction, just to recap, is the bending of light around objects, which is a property shown by waves. And interference is when two or more light waves overlap to combine, and they can combine such that they cancel each other out, and they can combine such that they add each other up, which leads to a light wave of a higher intensity. So just to visualize the phenomena better, here's a quick description on there is a quick simulation on diffraction. If you can see my screen. You can just turn this on and you can see that the laser is passing through a hole, but in the end, there's a very interesting diffraction pattern which is made at the end, which is caused by the various light waves bending around the hole and it causing it to form this pattern. So this is diffraction, and you can just play around here. I mean, if you increase the size of the hole, obviously you can see that the fringes are getting more close. And also one more and also you can look at interference. Interference is combination of the light waves. So as you can see, you can just see here they're not waves, but it's like exemplified by drops of water. You can see this water, this tap is making waves, and if you turn the other tap on, yeah, you can see that there's like there's interference here where the two waves are adding up. And there's also destruction where the two waves are getting cancelled out. So these are interesting phenomena of the wave nature of light. And also, when you have to look at light, you also have to look at the particle nature of light. Particle nature of light, just everybody knows about it. It is exemplified by photons, and it was discovered by Einstein in his photoelectric effects. While the particle nature of light is important in the context of telescopes, is that it enables precise imaging in telescopes because detectors use detectors to capture photons, and the capturing of photons enables for higher resolution observations. And yeah, this was just about light and which helps us to observe images in telescopes. But now let's just look at some basic definitions about telescopes before we jump into some of the more detailed topics. So initially, aperture. Aperture refers to the diameter of the lens or mirror of the telescope used to collect the light. So I mean, I'm pretty sure everybody knows like telescopes, you work on lenses and mirrors. So aperture is just the diameter of the lens or mirror. Then spherical aberration. Spherical aberration is a loss of the definition in an image because of the varying geometry. So you can see this on this video that in this video you can see the light rays they are getting refracted differently from each side of the mirror. So you can see that the top of the mirror has a slightly larger focal length than the middle of the mirror. So that is why that is why there is no single focal point of the mirror which causes a distortion in the images. So this is how spherical aberration works. Basically a defect because the shape of the lens is not a perfect sphere and has different refractive indices. Then there's also chromatic aberration. As you know, white light is made of 7 colors, and each color of light has varying refractive indices for various wavelengths of lights. So as you can see in this simulation which I've turned on here, that the red color has the red color seems to have a higher focal length than the other colors, and that is why there's a best focus. There's no accurate focus which we can make out to be. So these are two defects caused by these are two defects which are caused by images, which are caused by light and different properties of lenses and light. Then also there's the plate scale. Plate scale is defined as the angular size of the object per unit distance. So this might be confusing at first, but if you look at it, when you form an image on a telescope, it subtends an angle, and that angle subtended to the distance covered on the screen of the telescope is known as the plate scale. And there's also the focal ratio. The focal ratio is the ratio of the focal length to the aperture of the primary lens or mirror. And so after that, it's pretty intuitive to understand that lower ratios yield brighter images, and like f by 4, and higher ratios they probably don't yield images as bright, but they definitely offer a greater depth of focus. So this is about some basic definitions which we'll need in the following presentation in the yeah. So just a sec. Yeah. So now, before we get into how telescopes work, let us have a brief look at the history of telescopes. Just a sec. Yeah. Yeah. So let's look at the timeline of the telescope. So the first telescope was made by this guy called Hans Lifferle in 1608, and it just used basic curved lenses to magnify objects up to 3 times using just the basic laws of light. And he was actually a spectacle maker, and he used to craft like binoculars for the government and to help in wars and stuff. So he just stumbled upon this discovery of the first telescope, which was used to magnify objects. So after him, yeah, just a sec. Yeah. Then after Hans Lifferschi, you had Galileo Galilei, who, as we know, was a pioneer of telescoping. He used his invention to just look at the night sky, and he also improved upon the design to work for a higher magnification. So the first version of the telescope which he made, he could view up to 8x magnification also, and they changed up to 30, which changed up to 30x. And he also saw moon. He also could observe the moons of Jupiter. He observed the rings of Saturn. He saw amazing details of the moon. He observed the craters of the moon, and he also, of course, used his observations to prove that the Earth is moving around the sun and not like sun moving around the Earth as they previously thought. So as you can see here, this is like some interesting diagrams which you drew. So the big circle you can see is Jupiter, and the other small stars you see are the moons of Jupiter, which Galileo observed in his telescope. Then you have the Keplerian telescope. After Galileo discovered his telescope, Johannes Kepler made many modifications to the telescope, and he used a concave lens instead of convex lens, and this allowed for a much wider field of view and much greater eye relief, which Kepler modified. And you can see a image of a Keplerian telescope. It's just an illustration, but they used to be huge at that time. Then, of course, you have the Gregorian refracting telescope, which is the model which we even followed to these days. So this guy, he designed a telescope with the parabolic primary mirror. Why parabolic, you may ask? He thought that because of the mirror being parabolic, there would be no spherical aberration, because as you saw in the previous slides, that spherical aberration is caused by like uneven shapes of the mirror. So he just used a parabolic mirror. Uh, Hello?
Yeah, you're audible.
Wait, just a sec. My screen just a sec. Yeah, I don't. Can you see my screen still?
Yes.
Yeah, I don't know what happened. I'm sorry. Yeah, we were on the refracting telescope. So he envisioned that a parabolic mirror will be able to eliminate chromatic aberration and uh, spherical aberration, but he could not eliminate chromatic aberration. So after this, we of course get to Sir Isaac Newton. Sir Isaac Newton was the first person to build a reflecting telescope, and he solved two problems with the telescope at his time. Because there were no lenses, there was no chromatic aberration, and the color was not distorted. And so that was a huge advantage. But he was not able to correct spherical aberration, by which were caused by the round mirrors. So yeah, this was a revolution in the world of telescopes. Then you go to Chester Moule and his achromatic lens. So Chester Moule developed an achromatic lens with the goal to get rid of chromatic aberration. So it basically, as you can see here, it involved two pieces of glass with different refractive indices, and both of them just converge to give together a pretty sharp image of the object you wanted to see. And this resulted in a refracting telescope with little to no chromatic aberration. After that, you see the first astrophotograph, which was made by John William Drape. He made a very detailed photograph of the first of the full moon. So he basically just exposed his image to for about 45 minutes, and he could emerge with a very nice astrophotograph of the moon. This is also like what this astrophotography is really cool, and this is where it all began. So this is interesting. And then you look at 1937, you look at the radio telescope. The radio telescope was made by Carl Jansky, and he just got the idea that maybe you can look at radio waves and just not visible light to see the telescope. Yeah, somebody had a doubt. I saw someone's hand raised.
Your presentation is not varying. It's not
Ma- It's not.
It's not changing.
Oh, what slide can you see now?
We are seeing the 1663, the Gregorian refracting telescope.
Oh, just a sec.
Yeah.
Now?
No, it's not changed.
Okay, wait, let me just try screen sharing again.
Sure.
So sorry for that. Yeah,
Yeah, it's
now?
fine. It's fine.
Yeah. So this was, so I was at the achromatic lens. I'll just summarize this. So he developed a lens which removed chromatic aberration by using two different refractive indices of glass, which led to a much sharper focal length. And then you have the first astrophotograph, which was made by John William Draper. And we were at the radio telescope. And this guy had the novel idea of observing radio waves, but he obviously had very poor resolution images initially. But radio astronomy, as we know it today, is amazing and one of the most developing fields of astronomy. So this is where it all started. So yeah, this is about the brief history of telescopes. And then let's go to the types of telescopes before we go to anything. So telescopes, as we saw in the history of telescopes, are of like four types, four basic types. They're of reflector telescopes. Reflector telescopes use mirrors to gather and focus light. So there's a primary mirror which collects the light and it just refracts it back to the secondary mirror, as you can see here on the image above. There's a light path. The primary mirror, it refracts the light to the secondary mirror, which goes to the eyepiece, which is what we observe. Then there's refractor telescopes. They use lens to gather and focus light, and they are of a very simple design with an objective lens at the front and an eyepiece at the back. You can see the animation here on the video. Yeah, so you can see rays of light. They converge. They such that they lie on the focal length of the secondary lens, and you get a sharp image in the end. It's a very basic. It's a very basic working. So this is how refractor telescopes works. Then, as we saw, parabolic telescopes, they converge parallel rays of light to a single focal point, and they're excellent in resolving fine details again because you eliminate spherical aberration. And you also have elliptical telescopes. Elliptical telescopes are just more compact in shape, and you can have them in smaller tubes, and that is why elliptical telescopes are preferred over parabolic telescopes these days. So yeah. Just before we go, this is a montage of telescopes actually, which I thought was pretty cool. So these are just all the telescopes which are through history and some of the most iconic telescopes. This is the radio telescope at GMRT. GMRT is this place near Pune, which actually Kritika makes a trip to every year, and it's fascinating how the machine works and how it's able to capture images. And you should definitely come to the trip if you get the opportunity to. It's fascinating. So yeah, this is one of the radio telescopes at GMRT. The second image is like one of Einstein's telescopes, one of his reflecting telescopes. Then there's a Hubble Space Telescope. Of course, it really needs no introduction. Then on the bottom right, there is the Chandra X-ray telescope. It measures it sees light in the X-ray wavelength, and it is in deep space, which and has captured some glorious images. And then the other two are we will just come to them in a minute. These are the telescopes we have in our storage, and yeah, they are of two types, which we'll just come to in the next slide. So as we saw in the previous images, there were two telescopes which we couldn't name, but they were of two types. And they were not really of two types, but they were of two mounts. Mounts is basically the stand kind of on which the telescope is placed on, and they are of two types. So they can be of azimuthal or equatorial. So azimuthal mount moves up and down along the altitude and left and right along the azimuth. It's a little difficult to visualize. So let's just see this video. Mm, yeah, so this is how it is. It can move up and down, and it can also move left and right. So if you're observing a star, you can like change the planes in two directions, as you can see here. So this is an azimuthal telescope. it is really easy to set up, and it's user friendly and usually for casual use. And yeah, it's best for moons, planets, and other terrestrial viewing. Then we also have the equatorial mount. Equatorial mount, so what it does, it's a really ingenious method. You have one axis, it is aligned to the North Star. You know the North Star is exactly at the north, as at the geometric north. So you have one plane along the North Star, and the other, and you can just make the other, and you can just place one of the other lenses to one star, and as the Earth rotates, you can just follow it with the with the uh, with the mount. So as you can see, one is pointed towards the pole, and then you can just rotate it so that you have the focus on one star. It is usually for astrophotography and advanced astronomy, and it has really precise tracking, and it is for stars. So you can see this in this visualization here. Yeah, so yeah, you have one axis which is fixed to the North Star. Which is fixed to the North Star, and then from the other axis you can just move so that you have the stars you're trying to observe are under constant observation. So this is how an equatorial mount works. But what about choosing the right mount? So again, if you are just looking for casual use, you can have an azimuthal mount, and for astrophotography or precision, you use an equatorial mount. We at the Kritika inventory have both of the mounts, and I think when the sky gets cleared and when we have our regular Friday night sessions to observe, you'll get to see both of these telescopes in action, and you'll get a very nice idea of how they work and how they move and how they help you observe stars once you know the stargazing session starts. I mean, it's raining unfortunately now, but yeah, hopefully soon. Yeah, so yeah. So then, now that we have seen how telescopes work and form, let us look at some defects in image forming. So we saw diffraction previously. Diffraction just limits the resolution of image. And we have also looked at chromatic aberration before. Chromatic aberration is, as just to recall, is different wavelengths of light having different refractive indices. So on the right here, you can see this image of Jupiter, which is just really distorted just because there are different wavelengths of light with different focal length. And you have these color saturation around edges. And then there's also spider veins. So I mean, I think in one of the previous slides you saw that in reflecting telescopes, the secondary mirror usually needs to be held up on the telescope. So like once you hold the telescope up, you also need something to hold the telescope up, like right, obviously. So as you can see on the bottom right, you to hold the telescope up, you need these spider veins, and these spider veins are really thin and made of metal, and they usually hold a secondary mirror, and they can cause diffraction effects and can make the view unclear, as you can see here. And then in the end, you also have spherical aberration. Spherical aberration is lens or mirror with spherical structure causing irregularities in light, and it can be solved using non-spherical lens, as we saw in history of telescope. So these are the basic defects in image formation which we encounter on a day-to-day basis while looking at stars. And then at the end, let us look at the most exciting topic probably of all. Let's look at space telescopes. So space telescopes are placed in space, obviously, but they're placed in space because they need to overcome atmospheric distortion, and they need to provide clearer images of the star. Because on the ground, when you there's a lot of light pollution, the atmosphere diffracts a lot of light, and basically you don't have very clean data when you're on the ground. So the view is very obstructed. But in space, if you place telescopes, you get really sharp images without any atmospheric interference. And you also have full spectrum coverage on the top. You have UV, X-rays, gamma rays, and everything. And also, obviously, in the sky, there's no interruption from day, night, or weather. And let us and yeah, and then there's some key space telescopes we should look at. There's the Hubble Space Telescope, the Chandra X-ray Observatory, and there's this Spitzer Space Telescope for infrared observation, and of course the James Webb Space Telescope. And to look at some of these space telescopes in more detail, let's look at this brief presentation I made on them. Yeah. Yeah. So let us start with the Hubble Space Telescope. So this is a photo of the Hubble Space Telescope. And the Hubble Space Telescope is obviously one of the most influential and iconic objects ever launched into space. I mean, probably every other great astrophotograph you've seen is from the Hubble Space Telescope. The amount of information it has given us about our universe is insane and unparalleled, and it is just iconic, to just put it in one word. And yeah, so this is basic. This is the basic structure of the Hubble Space Telescope. It has 3 wide-field cameras, as you can see here, and it captures image in UV, visible and infrared light, and it's used to study distant galaxies and star clusters. The wide field camera, as you can see. Then there's also an advanced camera for surveys, and it is used for high resolution imaging and spectroscopic observations. What are spectroscopic observations, you may ask? Basically, when you look at any observation in the universe, it is just an observation. It is just light which is emitted by excitation and de-excitation of electrons, and the excitation and de-excitation of electrons are obviously different for different elements. And spectroscopy is the science by which you study the what elements, or what is the composition of that of the object you're trying to observe, using the characteristic wavelengths of light of the electron jumps. And it also contributes to research in galaxy evolution and dark matter. And then there's also the cosmic origin spectrograph, which is used for ultraviolet spectroscopy, which is basically spectroscopy in the UV range. And it also again provides insights to composition and dynamics of celestial objects. Yeah. Then let us look at some achievements of the Hubble Space Telescope. The Hubble Space Telescope determined the age of universe to about and refined it over 13.8 billion years ago. It did it through observation of distant galaxies. We'll come to that in more detail in the coming slides. But this was a revolution because this confirmed our knowledge about the age of the universe. It also helped us understand dark matter. We still don't understand dark matter yet because it's a very unexplored and new science, but it used this effect called gravitational lensing, as you can see here. So you can see light traveling out, and you can see the Hubble Space Telescope noticed that the gravities were acting as the galaxies were acting as lenses for the image. As you can see here, I mean, the light is coming, but it's again getting reflected, and that is not something which should happen just based on the mass of the galaxy. There needs to be a lot of other extra mass for which which is the requirement for an event like gravitational lensing to happen. So that is why Hubble Space Telescope observed this gravitational lensing, and it helped us to know more about dark matter. Yeah. Then it also measured the expansion rate of universe, again through observation of different supernovae, and this also led to the discovery of dark energy, which is one more phenomena which also binds stars in the galaxy together. You'll learn more about it in the other courses of the learner space also. And also shed light on star formation. Star formation was a very mysterious and aloof phenomena, like till like the 1990s. But the Hubble Space Telescope just observed nebula formation in observed nebulae and star forming regions to see how star forms. And this enhanced our learning about the Hubble Space Telescope. So yeah, these are some really cool images which the Hubble Space Telescope observed. I think this is called the Pillars of Creation. Pretty much everybody knows about the Pillars of Creation. And yeah, it's one of the most iconic astrophotographs taken. This is yeah. Then this is the Crab Nebula. I mean, if any of you happen to do the Kritika convener assignment, this was one of the images which we had to process. And yeah, this is the Crab Nebula. It's a star forming region. And this is a butterfly nebula, which is also a really cool astrophotograph that the Hubble Space Telescope has taken. Yeah. Then this is interesting fact about the Hubble Space Telescope. So actually, 2 months after its launch in 1990, NASA found that the Hubble Space Telescope had a problem with its main mirror. So I mean, the problem was, in human terms, it was really small. I mean, the mirror was off by about like 5,000 nanometer. But Hubble Space Telescope had to be so sensitive that you couldn't have an error of about 20 nanometer. And this error just escaped all 10 years of testing of the Hubble Space Telescope. And once it was launched in the sky, the scientists were just shocked because the images which they gotten were really blurred, and it was basically useless. NASA was being criticized for just making a failure after spending millions of dollars. But again, we are engineers. We always innovate. So NASA came up with this camera equipment with built-in corrections, and it's called CoStar. So basically, it acted like glasses for the telescope. So so that it would focus light well. So these fixes were installed in almost a 7 hour long spacewalk in the Hubble Space Telescope in about 1993. And after which you can see, so this was the image of a galaxy before the correction by the CoStar, and this is the image of the galaxy after. So you can see just the vast difference after the image correction. This is also a testament to human ingenuity and just our spirit of never giving up. Even after you've made a mistake, you just buckle up and find out the solution. So this was something I really found fascinating. And yeah, this was the testing of the CoStar. It seemed like a nice image. I mean, this is how they were like practicing on actually putting the CoStar on the Hubble Space Telescope. So I think that's all about the Hubble Space Telescope. And now let's look at the James Webb Space Telescope. So in like after the Hubble Space Telescope was launched, astronomers realized that okay, Hubble is not going to do it. It has a lifespan, and well, as technology developed, we noticed that we can do a lot more cooler things with telescopes. So that's why scientists thought of the James Webb Telescope. A lot of agencies around the world combined, and they formed this James Webb Telescope. It is much more advanced than the Hubble Space Telescope, and it was just and the objective was to find out more about the mysteries of the universe. It was launched in late 2021. So let us look at some of the scientific objects of the JWST. The first main object was observing the first galaxy and study and basically help us find out more information about the Big Bang and other dark matter and dark energy phenomena. It also shed light on early universe and early structure emergence. It is also used to characterize exoplanet atmospheres. And by observing exoplanet atmospheres, we can look for potential life, and we can also study about the atmosphere. We can study the conditions and if they are suitable for life. It also one of the objectives was to understand the conditions necessary for life, which involved investigating star and planet formation and observing young stars, and also the formation and evolution of stars and planetary system. Basically just analyzing organic molecules and chemical processes in star formation regions, and which will help us to find out more information on how life originated on Earth, and also about how stars originated, just to find out about all of this in more detail. Yeah, so this is about the objectives. And then let's look at some key features of the JWST. The most distinct feature is probably those huge hexagons you saw in the previous image. They're like 18 hexagonal segments which are plated with pure gold, and it is used for high sensitivity and resolution in infrared observations. This is the mirror of the telescope. Then there's also an infrared focus. The telescope has really optimized infrared observations and provides unique insights into the early universe, exoplanets, and the star and galaxy formation. And also, it has an advanced cooling system. So this is what something that was lacking in the Hubble Space Telescope. It is obviously equipped with a sun shield to block sunlight when it's directly facing the sun, but it also has instruments which maintain the optics at cold temperatures, which help it to observe faint infrared signals. Otherwise, heating and irregular heating was an issue in early space telescopes. So yeah, this is about the key features of the Hubble Space Telescope. And so let us look at some scientific achievements of the JWST. This is pretty recent and just happened in the last 2 years. This is really exciting if you are even looking at a career in astronomy ever. So it obviously took the clearest picture of Neptune ever taken. So as you can see here, this image is stunning for multiple reasons. You can see Neptune in its blue color, and also Neptune was theorized to have rings. It was observed to have rings in just like a couple photos before, and this just confirmed that Neptune's rings. You can also see the clouds on Neptune, and also you can see some of its moons. So this was the clearest image of Neptune we have ever taken from a space telescope, which was revolutionary. It also took the most detailed photos of exoplanets which we have ever taken. So exoplanets before the JWST were captured for only like 20-25 times, but after the JWST, you could take very clear images of exoplanets on demand. So you can see, like, you can just look at a star and you can just look at the images of the exoplanets, which was amazing for its time. Then you also have Then this is also another interesting fact. In July, the James Webb Space Telescope took an image of this star. It showed diffraction pattern and these concentric rings, which were shaped by the star and its companion. So there are these dust patterns which they studied. You'll actually learn a lot more about these dust patterns in some of the future courses, probably about CFIDs and stuff. But they observed these dust patterns and diffraction patterns in this star, which led to a lot of new exploration about why these dust patterns happen in dying stars. Let's not dive too deeply into it because you will cover this in some of the future courses. But yeah, this was an amazing discovery with the James Webb Space Telescope. So you can see the diffraction patterns of the light on this image here. And also, it observed Saturn's moon. So we have known for a long time that Titan, the one of Saturn's most famous moons, has ice and rivers and lakes of liquid methane and ethane with a pretty thick atmosphere. In November, the JWST actually captured images of Titan's atmosphere, and it revealed some clouds over the atmosphere. As you can see here, yeah, so you can see the bluish tints over across the sphere. So these are some of the clouds that the JWST observed over Titan and the Sea of Titan. And this was something which we had not observed before, and this was revolutionary for the time being. So yeah, that is all about telescopes from my side. Thank you so much for attending the presentation. And if you have any doubts, please let me know. I'll be happy to answer them.
Yeah, if anybody has any doubts throughout the slides or anything just related to telescopes in general, and not just doubts, even just random info, if you want to share, the stage is
Yeah,
open.
just anything you want to share or
It's a
do,
good
just
time to
please
speak
let me
up.
know. Yeah.
Okay, I think you did a good job at explaining everything. So nobody has any doubts.
Yeah.
Then.
Yeah. If you have anything, you just hit me up on the WhatsApp group. I'll be
Yeah,
happy to
and
discuss or
obviously
answer.
there is the doubts channel on the our team, and
Yeah, of
it's
course.
always open.
Yeah.
Apart from this, I would like to mention again that this presentation is not a substitute of reading the material that we've already provided. The material will provide you with a lot of more insights about each topic. This was just to build more enthusiasm for you guys and, just get to know random trivia about the stuff you're about to read. So this was it about telescopes, and most likely we are going to have the next session tomorrow on celestial mechanics and gravity. So I'll put up an announcement, and this is just in informal announcement. But yeah, I hope you guys enjoyed the session and look forward to the next one.
Yeah.
Any
If you have
feedback, any
anything,
doubts?
yeah, if
Yeah.
you have any feedback or any doubts, please let me know. But otherwise, thank you so much for attending. And yeah, please look at the modules which we have refined, and hopefully you get to learn a lot of new stuff from the modules. Yeah, thank you so much for attending. You can leave if you don't have any doubts. Yeah, I guess we can end the meet.
Okay, cool. Thank you.
Wait, I think there's a doubt. Adeep? Yeah. Oh wait, he just left, I think.
Yeah, I think
That
it
was
was.
probably a mistake.
Never mind.
Yeah.
Okay, cool. So
Yeah.
let's meet again tomorrow. Thank you.
Yeah, let's meet tomorrow. Yes. Thank you so much for attending, guys. I hope you had fun.